This is truly one of the most important physics experiments that ever happened. This that we're going to recreate now is effectively the method that can only be explained in a certain way and changed our ideas on how we thought about light. In the end, it's what got Nobel Prize for Einstein for his third paper that he published in the same year. So 3 important papers. One of them you may all have heard of, relativity, didn't get the Nobel Prize. The other one, proof that atoms existed, didn't get a Nobel Prize, but this one did. The third, or actually the second paper, was his theories of light and the photoelectric effect. Okay, so we're going to recreate basically the instruments that, or use the instruments that he had at the time to show you what's going on. What we've got here is a thing called a gold leaf electroscope, and it's an insulator, and inside it has a forked end, a piece of metal, and on it we have a little piece of gold that, if I hold a charged object near it, you should be able to see kicks a little leg up. Okay, it repels. So we can measure how much charge it's got by seeing how far the little leg kicks out. So we can measure amounts of charge. And obviously it's very delicate because I'm not exactly doing a lot to it. I'm just holding up a little bit of charged plastic nearby. So I'll introduce you to that, but the ideas that are important about this is that we have on the top of this the actual conductor that is linked to the bottom. I can take it out, but on the top of it I've got zinc, and for everybody from GCSE will know that zinc is quite a reactive metal. So this effect does work with other metals, but zinc or anything more reactive than that works really, really well. So because it's reactive, we need to take the layer of oxidation off that tends to build up on the top, and so that should work much more easily. Now, effectively, the photoelectric effect is the idea of light, and it had been discovered already, noted already. Heinrich Hertz, when he did his experiments to discover that radio waves were electromagnetic waves and therefore make a few connections in the story of light, or the story of the development of the idea of light, we had some pretty strong ideas by now that radiation was really well explained as waves. Unfortunately, this proved that there must be another way of explaining it as well, because you cannot explain this with wave theory. So what we've got here is I'm going to charge up a little indicator, so my little electroscope here. I'm going to charge it up, and what I'm going to do is I'm going to repel all the charges away. If I earth it, then you can see the thing drops down, the gold leaf. I take that away, and then what I should end up with, let's do that a bit more, is that I should be able to get a nice large charge, a nice big kick out on my thing there, on my gold leaf. So what I found was that if you have an ultraviolet source like I've got here, under ultraviolet light conditions, what happens is when we hold that on top, and I just check I've got the right type on, yes I do, then as I lower that down and expose that to ultraviolet light, the leg drops right down. The charge on this escapes. I'm not touching this, and yet the charge seems to have escaped away. Okay, so let's just run that through again and do this a bit more slowly. What effectively we're saying is that the light seems to make the electrons escape from this piece of metal that's suspended in the middle. Okay, it can't get through the wooden case. This is all insulation. It's basically a floating piece of metal that I can charge up. So if I just charge that again, okay, leg sticking right up, plenty of charge on it, and as I say, put the ultraviolet light source near it and turn it on, then what will happen is that charge slowly leaks away, and it's just completely gone in about a few seconds. Okay, and there was a lot of charge on that. Now, the interesting thing is, we can explain that. You know, our electrons that are in here have enough energy to escape. Okay, so the light is giving those electrons energy, and because of that they can ionize those atoms. The electrons can escape from their shells of the atom and they can actually leave the metal. They can jump out into the air. You're ionizing the air with the charge. Okay, that's not genius. The interesting thing is it doesn't always work. Okay, so first things first. If I charge this in a different way, okay, so actually leg kicks up, but I'm going to put the charge that's on the polymer onto it. Okay, so I'm doing the opposite. I'm actually scraping the charge off here onto here. Because this is acetate, what this means is this is now positively charged. Okay, if I do that. If I then put on my ultraviolet source and put it right over it, nothing happens. Okay, there's no charge escaping at all. So that was one observation. Positive charge doesn't seem to escape, only negative does. So I can just move that back, and I'll earth that. Okay, so I'll let the charge escape through me. If I induce a charge instead, so I take my positive, I repel my positives down to the bottom, I then actually touch that, the positives effectively manage to escape. I've now got the opposite charge. I've managed to put on the opposite charge to what I had before, so I've got a negative charge on. And as I say, if we put the ultraviolet light over it, that just fades away, so it escapes. However, if I try with normal light, okay, so a light bulb here, what I've got is a way, way brighter source, a much higher power source. So if I charge that, as we did before, if I use a bright source, according to wave theory, I'm adding a lot of energy. So I hold this over here, shine it right on the top, there's enough energy shining on that for it to escape. But it's not. Okay, this light is not right. This light isn't doing the job, even though it's nice and bright. And it doesn't matter how much I turn this visible light up, it's not actually going to make this happen. And if I try this with redder light, yellow light, it doesn't work either. Okay? I need ultraviolet light. And this is effectively how leaves work. This is how leaves get their energy to photosynthesize as well. So I'm going to turn back on my source. But this time, I'm actually going to use a long wave source. So I'll clip this through, and what you'll see is even with one ultraviolet light, and I can see the bulbs on from the end, so it's giving out a nice blue glow, blue-purple glow, and ultraviolet light as well. It's not actually making any difference. My electrode's not going down. But if I swap it to high frequency light, high enough frequency, then what happens is charge has just escaped. Okay? This is the photoelectric effect. This cannot be explained by adding more and more and more energy. It can't be explained by turning up the intensity of the light. It can't be explained by the fact that it's just light and it's electromagnetism. This can only be explained if the light reaches a certain threshold frequency. And if it's above that frequency, if I use high frequency ultraviolet light, if I use X-rays, if I use gamma rays, they're all ionizing. Yeah? For those that know a bit more about ultraviolet, what I've got on at the moment is ultraviolet C. This is the stuff that tans your skin, it ionizes your skin. If I turn it down to UVA, which is the low frequency, it doesn't work. Okay? So it needs to reach a certain level for it to work. If I change the metal, then I need a higher frequency if it's less reactive. The more reactive the metal, the lower the frequency I need. But there's a certain frequency, below that it does not work. Above that it does. And that can only be explained if we start thinking about light in a different way.